Okay, so this is to let you understand the concept of electricity. I will begin with a story about electricity. Now, so in this situation, you notice that I've drawn a drawing of a house, alright, and there's an office, there's a factory, there's a farm, and then you notice there's a path. So what happens is that in this story, you are a person coming out from the house over here, and you have your friends with you or your family members with you, and each one of you will come up from the house, right? And then you will proceed along the path. So you notice that you go into the office and then you'll do some work, right? And then after finishing your work, you notice that there are two paths for you to go, and you will carry on going through the path. Once you're done with the path, you will walk back or cycle back, or how you move, doesn't matter. Eventually you go back to the house. Now, so the story is as such. It seems like a rule of the game is this. When you come out of the house, you have a certain amount of energy, say 12 joules. So you have 12 joules of energy. And at the end of the day, when you return home, I've only drawn 3 people. So the 3 of you, each one of you must have 0 energy. And this is where you sleep. Right, this is the place where you will eventually sleep so as to recharge yourself. Now, so when you move on to the office, there's only one path, so you notice that you have 3 people who will then enter the office and do work. Now, before you enter the office, you notice you have 12 joules of energy. Well, the office is probably a tiring work for you, so probably around 8 joules of energy required. Right, 8 joules is required. So when you exit from the office, you now have only 8 joules. Sorry, you only have 4 joules of energy left. Right, because 12 joules of energy is what you have initially. You use 8 joules of energy, so right now you are left with only 4 joules of energy. Now, so of these 4 joules of energy, you realize that you cannot go home yet because you need to go home with only 0 joules of energy. And in front of you, you notice there are 2 paths, one factory, one farm. And so these 2 are going to use up all your energy before you go home. And some of you might prefer to work in office, say for example maybe 2 people prefer to work in office. So as they enter the factory, they have 4 joules of energy. So one person will now go to the farm with 4 joules of energy. Right, so the factory and the farm both will require 4 joules of energy in this case. So 4 joules of energy is required. And after which, when they exit, notice that 2 of them exit from the factory. Each one of them have 0 joules. One of them will exit from the farm. You will be left with 0 joules. Now, so at the checkpoint, at this point in which the path converges again, you notice that again you have 3 people at this path, each one of them having 0 joules. And they will go home, they recharge, and then they will actually gain 12 joules over here. Now, so this is the whole story, right? It seems weird, but this is basically just an analogy. Okay, this is just an analogy for us to understand electricity. Now, I'm going to write in green what does each of this thing represents. Now, so the sleeping here is actually not really sleep, but basically each of these people is a charge. Each of the energy they have is actually known as your potential. Alright, and you notice that the difference here between 0 and 12, this is where they gain energy, right? So since they gain energy, this is actually similar to your electromotive force. The amount of work done, the amount of energy that they provide a charge, right? So if you recall, your EMF is actually work done per unit charge, which is actually the amount of energy given to each of the charge. So this 12 joules that you see over here is actually the amount of energy. Okay, so this energy is now known as a potential. So the energy per unit charge that they will consist of. Now notice, since there's only one path, right? Since there's only one path along here, and you have 3 people, which is equivalent to having 3 charge, notice that at any point in time, the charge here is always the same. The number of charge is constant throughout. This actually should remind you that I total is equals to I1 equals to I2 in a series circuit. Because there's only one path, the charges can only flow in one possible path. So all the charges will be on the same route. Alright, and then we take a look at this. Now we notice that before entering is 12 joules. After it enters, it's only 4 joules. So what is the difference in the potential? This is known as the potential difference. And you notice that the potential difference is actually equals to 8 joules, right? 8 joules per 1 coulomb of charge. So this is your potential difference. Right, now I talk about energy, I'm using joules, and you notice that for potential difference is actually in terms of volts. So this is actually equivalent to 8 volts, because for every 1 coulomb of charge you need 8 joules of energy. That's the reason why potential difference is having unit of volts. So of course, if you remember, the amount of energy each one of them have, each charge has, is actually considered as potential. So the potential before entering the office, potential after entering the office. That is what is meant by the potential difference. So we move on. The next part, you notice that over here there's a junction. This is actually similar to your parallel branch. Right, so this part is actually parallel branch. So in parallel branch, you notice that the potential at each point is the same, 4 joules, because along the path from the office to the farm or from the office to the factory, there's no resistance required. So no energy loss, no work done required, so each of the charge actually has the same amount of energy. So this part actually reminds you of the fact that across parallel branches, the potential difference is the same. Right, so some of you actually realize that we call it they share the same potential. So if you compare before and after, it will be the same amount. Right, before and after, the potential difference across is the same. Right, 4 joules per charge required. Right, even if this is factory and this is the farm, this will be different. Now, so of course you might be asking or wondering, then how do we know about the resistance? So if you recall, based on the formula that R equals to V over I, the potential can be the same, but because of difference in the resistance, the current will be different. And if you look at this diagram over here, which one do you think is having a lower resistance? The farm actually has 1 coulomb of charge, or rather just 1%, compared to the other side, the factory having 2. So we can actually take it that the farm, I'm going to put in inverted commas, has more resistance, therefore less current passes through it. Okay, so this is how you can understand it. And after going through the parallel branches, you notice that the current once again will join back together. The charges will now flow together. So there are 3, and notice that this is actually the same as the initial current that you have, right, at the start. This shows you that as long as you're in a series circuit, the current is always the same. I total equals to I1 equals to I2. And by looking at this splitting in the parallel branch, where the charges actually get to choose which path they want to take, you we'll be able to see that the current for a parallel branch, right, the current for a parallel branch is I total is equals to I1 plus I2, etc., etc. Right, because the sum of the current in the parallel branches is equals to the total current. And at the end of the day, they must always go back to the battery with zero potential. Right, so the house is similar to your battery. Okay, so from here, I hope that you understand the idea why is it that the current is constant in a series circuit, but the potential difference across a series circuit is actually different. And you also realize that over here the house has 12 joules of energy, so each of the charge, each coulomb actually have 12 joules of energy. So when they go past the office and the farm, you notice that the potential difference is 8 plus 4, therefore it's 12, which is equals to the total EMF. So that will actually highlight to you the idea that your V total is equals to V1 plus V2 in a series circuit. Right? So this is for series. For parallel branch, your current is I1 plus I2 equals to I total. And in parallel branch, V total equals to V1 equals to V2. Right, so this serves as an example, a story to help you remember why does it work in a certain manner.